Mach 1, Mach 2, Mach 3 are terms you have probably heard before, especially in Hollywood movies. Maybe some of you already know they refer to speed. But have you ever really thought about what that exact speed is? Have you ever tried to imagine how fast these extreme machines are? Well, in today's video, we are going to dive into the meaning of Mach 1, 2 and above. In military aviation, explaining the transition from subsonic to hypersonic speeds in an easy to understand way. Jai Hind dosto, this is Prajesh and you are watching AirPra. The speed of sound refers to the velocity at which sound waves move through a medium, usually air. For example, in dry air at 20 degrees Celsius, Mach 1 means sound travels at around 343 meters per second. 1 meter means like this much. That means Mach 1, once again, Mach 1 means sound travels at around 343 meters per second. However, it is quite essential to note that speeds can vary based on temperature, pressure and humidity. In military contexts, subsonic aircraft refer to planes that operate at speeds below the threshold of supersonic velocities, typically cruising at Mach numbers lower than 0.8, which is approximately 274 meters per second. These aircraft form a diverse fleet utilized in both combat and logistical roles, spanning from reconnaissance and transport to close air support missions. Their design emphasizes endurance and versatility, allowing for effective deployment in various operational environments. Subsonic flight offers better stability and fuel efficiency, enabling sustained missions and facilitating precise aerial maneuvers. These aircraft leverage conventional aerodynamic principles to ensure reliable lift and propulsion, contributing to their widespread utilization in military aviation worldwide. Excluding high-speed fighter jets, all military aircraft, including transports, helicopters and drones, as well as civil aircraft such as airliners, helicopters and future passenger drones, are designed to operate within subsonic speed configurations. Transonic speed refers to the range of velocities near the speed of sound, where airflow around an object became increasingly complex. The airflow around an object occurs at a speed that creates regions of both subsonic and supersonic airflow around the object. As the aircraft approaches slightly above Mach 1, from around 0.8 to 1.2, which is approximately between 274 to 412 meters per second, it encounters aerodynamic effects such as shock waves and flow separation. This phenomena pose challenges in aircraft design and operation, significantly impacting stability and control. After the end of World War II, engineers began to pay special attention to designing high-speed fighter jets and carefully managing airflow to prevent performance limitations and structural stresses. Most modern jet-powered aircraft are designed to operate at transonic airspeeds, which typically range from around Mach 0.8 to 1.2. At transonic speeds, there is a significant increase in drag and asymmetry, leading to unsteadiness in the flow around the aircraft, especially when it exceeds Mach 0.8. Engineers employ various strategies to mitigate this drag, with swept wings being one of the most notable solutions. Swept wings are a common feature on high-speed aircraft, effectively reducing wave drag and enhancing aerodynamic performance in the transonic regime. Supersonic speed refers to velocities surpassing the speed of sound, beginning at Mach 1 and extending above but remaining below Mach 5 within a specified medium. Objects traveling at supersonic speeds generate shock waves, producing an extreme sonic boom characterized by shock waves and intense aerodynamic effects. Supersonic flight requires specialized engineering to manage high temperatures, pressure differentials, and structural stresses associated with extreme drag. Supersonic flight revolutionized aviation, enabling faster travel times and military capabilities. However, achieving and sustaining supersonic velocities demands advanced engineering and design, such as streamlined shapes and efficient propulsion systems. Despite its complexities, supersonic speed continues to drive innovation in aerospace, shaping the development of high-speed aircraft and exploration beyond Earth's atmosphere. Most contemporary fighter aircrafts are engineered to achieve supersonic speeds, surpassing the speed of sound. However, certain advanced fighter jets possess the capability of super cruise, enabling them to sustain supersonic flight for prolonged durations without relying on afterburners. Hypersonic speed describes velocities surpassing 5 times the speed of sound, that is Mach 5 or about 1,715 meters per second. That is roughly 6,174 kilometers per hour within Earth's atmosphere. It is important to remember that Mach 5 marks the starting velocity of hypersonic speeds. When objects move at hypersonic speeds, the airflow around them became extremely turbulent, creating intense aerodynamic heating and shock wave. Achieving hypersonic flight possesses substantial engineering obstacles because of the extreme temperatures and pressure involved, necessitating the use of sophisticated materials and propulsion systems. In simple terms, when an object moves at hypersonic velocities, the friction between the object and the surrounding air generates intense heat due to air compression and aerodynamic heating. These temperatures can reach thousands of degrees Celsius, posing significant challenges for materials used to construct hypersonic vehicles. Ensuring that the materials can withstand such extreme temperatures without compromising structural integrity is crucial for the success and safety of hypersonic flight. In short, these points to remember. Subsonic speeds below Mach 0.8 are around 274 meters per second. Transonic speeds, typically ranging from Mach 0.8 to 1.2, which is equivalent to 274 to 412 meters per second, bring a mix of subsonic and supersonic airflow. This creates challenges such as shock waves and higher drag. Supersonic speeds exceeding Mach 1 but below Mach 5 range from 412 to 1715 meters per second. Aircraft at these speeds generate shock waves and sonic booms. Hypersonic speeds exceeding Mach 5 range from approximately 1715 to 3430 meters per second. Researchers consider this regime to extend from Mach 5 to Mach 10. Hypersonic aircraft speeds cause intense airframe heating and navigation challenges, demanding advanced thermal protection and sophisticated flight control systems. Besides these speeds, if you want to explore high hypersonic and re-entry of space shuttle or missile velocities, please log into airpra.com. I have also included a link in the description below. Alright then, this is all about getting a general idea of speeds, starting from subsonic to hypersonic. I hope you will remember the differences in speeds. Therefore, I request you to like the video, subscribe to this channel. Until then, take care, stay updated, and bye-bye.